Audio check. Seems good. I'm just cleaning up what I was working on the rest of the week here. You can work with less buffers open. I had a lot of buffers open, didn't I? Jeez. Okay, almost there. There's probably a more efficient way to do this. Let me look. Emacs, buffer list, those buffers. There's got to be a shortcut for it. I think that's what I was asking. Kill some buffers, kill matching buffers, kill buffer. Let's just try to kill some buffers. Let's try that. To do, this is, we'll keep this one. We'll keep shell, we'll keep scratch. Action, define, text edit, text quad, shaders, text quad, common code, color quad, spin constants. No. Sure, we can kill health. We don't use it that much. There. Now, buffers list is nice and clean. Phew. Okay. I think that means we're about ready to start. I don't know why Windows can't lay out windows like that. It says in the name. Okay. So in our to-do list, we definitely need to compile pattern to NFA. We will need to generate some output eventually, but we don't need to do that right now. So go to our journal. We'll bring up a new item for today. What's it, the 2nd? Happy August to everyone. Okay. Notes. Okay. So, I guess it depends. I guess there's not anybody in the chat anyways, so maybe this explanation is unnecessary. We'll give it a minute. I gotta get my beverage of choice ready anyways. to our shell. Do a clean and debug build. All it does right now is read in our project file. Then from the project file, we figure out the tokenizer file and parse that one. So we can list out the project file is, we call it test.vb project. So here's our project. We've given it a name, test. We've said we're working in ASCII. Here's where our tokenizer is defined. Here's where our parser is defined. We probably should output the tokenizer rules after this. And the parser we're not going to do anything with for quite a long time. So let's go make that change real quick. Oh, guess it's in VB project.log. There, done. You know what we could do though? We can actually make this better. We can do this as push top. This is one of the reasons I wrote my own logging. Either one of these could set the can't. Think of all this log. There we go. Then inside of our what do we call this? VB tokenizer definition log. Okay. So the tokenizer rule, the thing that gets logged. Basically, I've always wanted to look at hierarchical structural data or call graph types of log statements. So managing an indent. Most log things just have the levels of logging. So I have a debug log level, and I also have one below that called trace, which is exactly what we are interested in. Boom. Indentations, almost exactly the way we want. Tokenizer rules. Is too much indent. Oh, I see. Haha. Tokenizer rule, there's no more prefix. We just rely on the trace debugger for that. There we go. Now it won't be super indented. Okay, so tokenizer rules pushed, but this tokenizer thing didn't pop the last time. So VB project. It is doing the pop. Oh, parser, I am, again, this is the whole point, is so I don't have to keep track of my indent. I just write a string, it figures out the indentation based on the level in the hierarchy. Boom, there we go. Tokenizers here. There's rules there. Okay, so each tokenizer rule has 4 parts. The token name, some actions it can take, and a regular expression pattern. And implicitly, so it's not stated here, you have the tokenizer rule number. So let's go ahead and log that. Rules and place back. I think that's it. Okay, maybe tokenizer rule dot HPP. Okay. Int underscore index. So we construct one, we need an int index. And where we set things. Okay, now each rule. Oh, let's see here. I just haven't done my stream announcement. What the heck? Getting carried away here. Oh, we should throw this up on ye old Twitch as well. Seems like there's almost always something I forget to do. Stream starting. Sometimes I forget to turn the power on my mic. Other times I got to change the stream title. Today it was posting the note. There we go. Oh, now we're all announced. And back here. Okay. so we set the index. We're going to go ahead and say when we clear, m underscore index is equal to -1. And then where we log, modulus 03D m underscore index. Why not? Okay. Other dot index. Oh, so are we in place back? M underscore rules dot size. Okay. Now our rules are numbered. This is important because when we generate code, we're going to define an enumeration with this as the name of the enumeration, and this as the value of the enumeration. Then we'll never have to do a string lookup unless we really want to. We can do everything by integer lookup. And these will be indices into tables. It'll be very useful having this mapping. Being able to say, hey, what happened with rule number 3? And we can actually ask that. Okay. So we could pretty print this a little bit if we wanted to, make the columns have a consistent width. Nah. It would be nice though. But I would have to do some work here to find out the longest name, the longest string of actions. I don't remember. I mean, it doesn't matter right now, but so we're just storing actions as a character, right? So that's okay for now. We're not using it, and we won't for a while. We have to go pattern to NFA to DFA. Then we can think about the actions. But that's fine. Let's do it. Let's pre-print this a little bit. Print it up a scotch. So first of all, VB tokenizer rule. Where we call log int name width int actions width int name actions and pattern width. So we won't have to pass any of them. Unless we want to. Format string Let's make it rather large. sprintf this stuff. Everywhere there's a modulus, we can put two modulos. And then modulus D name width, actions width, pattern width. Actions width greater than 0 or pattern width greater than 0. So we get our format string. So we're going to write into format, the format string. And then we can log this, which will be the format string that we computed. So right now we should see no difference. The standard rule log should say, hey, it's a 0 length. Let's just print it all the same. We did. Okay. And VB tokenizer definition. We're going to pre-compute some things. Int name width 0. Yeah. Actions width equals 0. Int pattern width equals 0. Okay, one other thing we could do. Int we'll just okay, int index. Okay, so for each rule, we can get the name, length is greater than width, and width equals length. Actions length greater than actions width. Actions width equals length. Finally, what do I call it? Pattern. Name actions regex. Okay, fine. Pattern width. It's len. Int rule count equals underscore rules dot size, while rule count is greater than 0. Index width plus equals 1, or just increment. And rule count divided by equal 10. Maybe that'll. Okay, then we come down here and we log it. Let's say tokenizer rule dot. So log also needs an index width. Okay. Instead of this, it looks like that. Okay. So again, none of this should be different yet, because we're not passing in any of those values. Let's make sure it compiles and runs. We're getting single digits, everything is not aligned. Okay, index width, main width, actions width, pattern width. Let's hope this works. Okay, so we're going to remove all the quotes. Really don't think they're necessary. Especially if you actually align things nicely. Oh, and they are correct. I think I want negative so that it's all left aligned instead of right aligned. Good. We could even output this as a table if we wanted to. Do we want to? We can. Is that what we want to do? We could do something fancy with a header. Actually, we should probably. Okay, equals strlen name. These are the defaults, basically. Strlen actions. Strlen pattern. Strlen index or ID. We'll call it ID. Then we can output something like this. Except instead of this, modulus something minus modulus D or string. Yeah, I think that's basically all of it. Oops. Except it will be the name actions pattern. Moving on output, so it's just more readable. Okay. ID name actions pattern. We can even compute a top and bottom bar separate sections. We might as well, right? Is that right? I think so. Char line is going to equal index width plus name width plus actions width plus patterns width plus 2 at the beginning, 2 at the end, 4, 7, 10, 13 plus 14, 1 for the null character. There's a way to do this, I'm 99% sure. Not centering. Left pad. Yes, modulus 5s, modulus 7s, I know about that. Modulus. Okay, so maybe actually this isn't that bad. Different line. Basically this. Except I don't know. I'm gonna remove the white space. Here, all of these would be plus +2 for the spaces in between them and the line. then sprintf into line format. So this will be modulus minus d. I think that's it. We'll just make that a second limit. Except this S doesn't need anything. I just literally pass empty strings? That would be convenient. Or am I overthinking this part? Hard to say. Let me think about the format string for a second. Let me just put it into line. No. Let's see what it looks like. Boom. Did not work the way we wanted. See if we can trick it into doing what we want. Okay, what if we do equals instead? Star. Vertical plus 1, 2, 3. Set of characters that are allowed to be in that. It's useless. Come on, people. Real information would be nice. I have to put spaces in so it knows to break it up. I bet it doesn't like that. There.
Stop it! Stop it! Stop it!
Hmm. I think this should be working. Minus 4s. So did I lose a modulus somewhere? Modulus equals minus d string. Let's see what it looks like. It's my format string is missing the print string is just missing those modulus operators. It should have been, yeah. So there should be a modulus right here, or right here rather. That's why we put a double in. This double is what makes this work. So where are these going? I'm going to put in a third one. Two, three, four. Yeah, that's what I thought. He knows what to do with the percent. So why, oh why? Where did this percent go? I'm printing into the string format the character plus modulus, so that will be reduced to just modulus, just percent, equals minus percent d, which is replaced by this number. Okay, well, apparently I'm overthinking this. We can just simplify. Line offset equals 0. Line at line offset equals plus. It's 0 uncount. We'll just do count. Count less than index width. That's 2. Plus count. Line at line offset equals one of these. Put in one of those. So the index width, it's a width. Then actions width. Pattern width. And one last thing. Delete line. And we'll see what happens. Okay, super close. I did not add the 2. Because I didn't add the 2, I added 1. That's It's fortunate to always got to overthink stuff. How's it going? Welcome to the chat, everybody. Okay, now this line will go here. No, it'll go here. Go at the top of the table, right after the header, and right after the last line of the table. Now we have a nice, clean, beautiful table printout. Boom, sort of. Let's go before that pop. Everything will be indented, aligned, tabular, beautiful. Okay. So there's our tokenizer rules. Why is that 3? I would expect 1 digit there. Tokenizer definition. Oh, I see. Index width less than 2. Index width equals that. We can even go ahead and put this in here. This is not like a performance critical piece, so boom. Okay. All right. Good. Little warm up. FitWriter, do you have any experience with the finance industry, especially working for like hedge funds, for example? No. Every time I've been on the verge of getting a job offer, they ask about my side business that I'm running with my brother-in-law. And they really, really want people to not have a side business. And I tell them I'm not going to do that. You can't dictate what I do when I'm not working for you during my off hours. And then I don't get an offer. So, nope, no experience there. What side business? So, my brother-in-law is an electrical engineer, and he's, long story. We have a angered gecko. Hey, welcome aboard. So my side business. My brother-in-law is very, very good at electromagnetics for high power transmission lines. And there's an industry of consultants that will analyze a power utilities lines for them. And some of the things are very easy to run, some of the analyses. One of them was very hard. It required setting up a full electromagnetic finite element analysis. And what you would do is you'd take it to the consultant. You'd say, hey, here's my line set up. Does this meet government regulations, yes or no? And they'd say, all right, that'll be 2 weeks and like $20,000. And 2 weeks later, you'd pay over your $20,000, and they'd tell you yes or no, and that's all. Maybe they tell you the actual amount, right? But basically, here's how much you're not meeting the government regulations by. Well, my brother-in-law and his professor worked out a cool new way to calculate it that's much more efficient. So it was a public paper. So I took his paper and we formed a company and we cranked out a piece of software that would do the calculation in seconds instead of weeks. And we sell that on our webpage to utility companies, power consultants, that sort of thing. That's the side business. I think it's pretty niche, but I also think that there's a lot of government regulations. So yeah, it's pretty cool. I'm not a really electrical engineer, so like if you want me to explain the math, I can explain what I did, but I don't know necessarily all the electromagnetic analysis. This particular problem is called the 5 milliamp rule. Basically, your car is conductive, the earth is conductive, and your tires are resistant. So what you actually have are two conductive plates with a resistor in the middle, which is called a capacitor. So when your car drives under a power line, the power line will energize your car, and when you step out of your car, you will discharge that static electricity in a single discharge. And the government has regulated that you're only allowed to build up 5 milliamps of current during that for that discharge. Anything more than that is unsafe. So you can build it higher. The higher you put the lines up, the less charge your car builds up. But then that can cost you more in concrete, metal. You're gonna have to use stronger materials. It's more expensive to construct a higher power line. So the power lines, the power companies want to build it right at the lowest level where it has that 5 milliamp rule met. So that's the actual calculation that we're banking our analysis tools on. So that's the side business. Still waiting for it to take off. We've sold some copies, but not really enough to not do it to do it full time. Getting ready for a new release, but yeah. So that's my side business. So I wouldn't give that up because I think if it takes off, like that's going to make me more money than working day-to-day job at some hedge fund, for example. Just need it to take off. Which unfortunately in this industry, marketing is the hard part. Like they don't read emails, they don't look in magazines. Like how do you get the right people that can make those purchases, software purchases, aware of the tool? So a little tricky. That's the side business. So where were we? Okay, so we parsed out our project file. We parsed out our tokenizer rules, and we're now printing out our tokenizer rules in a nice, neat, clean format. Perfect. So today, we need to crank through these patterns and turn them into NFAs, a non-deterministic finite automata. And just sends mass email spam. Yeah, we tried that. We may have gotten one cell out of that, but seriously, and okay, so my brother-in-law, he was a consultant for a power engineering company, and we sent out, well, he sent out thousands of emails, and then to a fairly targeted list, right? He wasn't just spamming everybody. It was people in the electrical engineering company who has a decent job title relative to what we're looking for. Yeah, certainly more fulfilling. That was a great project, pretty fun to work on. And then he quit that and went to work at an actual utility company. And he's like, I understand now why the email campaign didn't do anything, because every day he gets tons and tons of emails trying to sell him products, and he's like, there's no time. So you just, if it looks like it's a sell thing, you just delete it. So everybody's trying to spam the few power utilities companies to sell their products, and it's now over advertised, so there's no way to get in through email. Is line array 0 initialized? No. Yes, you are correct. Let's see here. Where's my line? Line len equals this mess. Line len plus 1. Line at line len equals null character. There, now we're null terminated. Yeah, so I fiddled around with f-printing a format string that would then f-print what I want, and it wasn't working. There was something about the pair of percent signs was disappearing instead of becoming a single percent sign in the format string we were generating. I'm like, fine, this isn't rocket science. Let's just hard code it. Doesn't matter. Yes, I should not terminate my string. So we've got a table. We need to turn patterns into NFAs. So I've already written this once, and I won't say it's great code, like this was me learning and experimenting. So, but there were certainly lessons I learned there, so we should probably take a look at that. What did I call it? NFA compiler? So the main interface is you have to pass in your rule ID, you have to pass in your token ID, then the pattern. So let's see here, let's split this. So here's the rule ID, right? The token ID we're going to have to figure out, because you can have, for example, multiple definitions for comment, or you might have keywords broken up across multiple rules. So I will have to blaze through this list and arrange them in a token ID, which isn't that hard. Then the pattern we have, and we will build an NFA out of that. So that's fine. Merge. So each of these rules in the NFA will be its own little NFA tree. And when we merge, we're basically going to take the NFA we generate for this sucker and put it as an alternation with this NFA. We're actually going to move, remember, we're not even going to copy. We're cheating big time. So that merge function does that. It says put source and destination together underneath an alternation. If somebody wants to ask what like regex are and how they work and all of that jazz, we can certainly dive into that. I'm just going to stream of consciousness otherwise. So we initialize things. Set root. There's a couple of different methods for that. I don't remember why. A couple of overloads for state and root. Scan the pattern. This is where we walk forward through the pattern, adding fragments. Deuce fragments. I've basically calls these things in order. So if you have a cardinality thing, it's going to take the preceding element and add a numerical limit to that. Concatenation, alternation. I did not have anchoring or like there's a lot of regex elements, features that we don't use. And it's not that we can't. In fact, I probably will do anchoring this time. I think it's useful enough to put in. And cardinality, there are things that I could put in, but I haven't yet. So cardinality right now is 0 or more, 1 or more, or 0 or 1. Those are the ones I support in this initial implementation. Patch fragment outputs, append fragment outputs. Okay. So this is kind of the initial pass at what would I built. There used to be another C++ streamer, don't think it should anymore, but he built something like this. Cool. I will look at his stuff. Yeah, again, and I'll be straight up with everybody. Writing a tokenizer isn't rocket science. You walk forward one character at a time, and every step of the way, if you know what to do with that character, you usually go into some sub-function which knows what to do with it, right? If you hit the number 0, you go down into your integer parser, and maybe if the next character after that is an X or a B or an O, you know that it's a hexadecimal number, binary number, octal number. If it's the number 3, then hey, then we're just working with a decimal integer, and you move into different sub-states, you know, different functions to continue the parsing, marching one forward one character at a time. It's not rocket science. This is fun for me, building these NFA, DFA compilers and emitting bizarre code. Let's see, does anybody... So this one actually is built on top of our own a tokenizer. So we generated our own tokenizer that is used in this other old project. A couple of helper functions. Here's where it starts. And it's all go-to. So once you hit this function, get our current character, go to state 0. Depending on what you get, C equals R, blah, blah, blah. Consume the character, move to state 1. Here's all the things that could possibly happen. And it's all go-tos. Everything is go-tos. So this generated 1,100 lines of code. And it does a few interesting things that we'll talk about when we get there. You love this stuff? Awesome. I feel like a weirdo sometimes. Like, I love tokenizer generators. And people are like, oh, what's wrong with you? No switch case? No. Go-tos are faster. Or they will be faster. Here's the point. Part of the reason I want to rebuild this whole thing from the ground up is as I go through each piece, the code I generate, I'm going to build in a lot of pound defines that say, hey, what if we use a switch statement? Hey, what if we use go-tos? Hey, what if we use lookup tables? What if we stream all of the tokens into a single vector and then pass that to the parser? Or what if we generate one token every time the parser asks for a new one, right? All these different ways that things could be laid out, could be built. Do we put actual functions in, function pointers, or like just single monolithic functions, right? And I kind of want to just see what the performance differences are between all the different cases. So I'm not guessing, right? So yeah, that's part of the plan, which means we're going to implement absolutely everything in 3 or 4 ways. How do you break out? I will show you. And again, this has been a long time since I've looked at this stuff. Accept in root. So if you hit an accept state, we go into this function, and this is basically, here's the rule ID we were in when we came here. Most of these are accept or reject. So at end, is that what we called it? Here's a function for saying, are we at the end? Well, we're not at the end. So there's your loop. Yeah. That's it. We just iterate until we're at the end. Until you, just keep going to the start of the loop until you're at the end. So if, for example, you're in the middle of parsing a token, when you hit the end, it'll do one last accept of the token. So that's what we're going to end up at eventually. Not yet. This is going to take us a couple of weeks, especially if we're only working on 1 day a week. So back to the NFA compiler. I'm fine with this function where it is. So let's see. Let's look up the NFA compiler that I built before. NFA fragment gets defined. Compile. Oh, so here's a resource if anybody wants to look up Thompson DFA construction. Let's throw that in the thing. Since in switch case, it's basically checking all the conditions one by one. Do you know how many states your NFA tends to end up with? Depends on the language. Let me see. Let's go into compiler for Billy. I remember where I put the binaries in this project. I didn't have things standardized yet. Star.exe. No, is it in the build folder? Have I done the /builds debug? Okay, so it runs. We will give it a file name of Billy, I guess. And we will tell it to, oh no, this is, we want to go into Bay. /builds debug Bay.exe. That looks better. So we can give it our file name of bay.bay. So this is the tokenizer specification for this that's built into this executable to be able to parse these files. So here's the NFA. So there's like 80 here. Yeah, there's like 80 in the main chunk. If there's a dash, that means we printed this out above to prevent full recursion. We'll note that 81 showed up before, but 80-ish. So that's the NFA for all the rules in this file, bay.bay. So this yields 80-ish states. Yeah. Well, yeah, and this is not for a fully featured language, right? So, yeah, for a fully featured language, you can have keywords and all sorts of weird syntax. So, but really, I mean, even for a fully featured language, maybe a few hundred states, it's fine for a modern computer. Okay. So yeah, this is what we're going to aim towards. So NFA compiler. I don't remember what the difference is between these two. I'll be honest. Or if I even used both of them. Set root is start state. Okay, that's why. No. Clear whether each state has been visited. Throw away the collection of states and add a new state. So really it's about passing through to add state. So what is the difference between these two? Here's a rule ID, a token ID. Yeah, I don't remember anymore. This is that merge we were talking about earlier. Not a copy. It is a move. I'll hop off now. Ingrid Gecko, thanks for popping in. Yes, I am curious to hear ideas about NFA simulation once I get there. Thanks for dropping in. Always appreciate you coming in. All right. Let's see. Where are we at? Part of me wants to just start copying things, but I don't think that's the best way to go here. This actually wasn't bad code. Most of this part was not bad. I am, however, using this UTF-8 buffer. So let me think about this. So what I use the UTF-8 buffer for here is taking the string and interpreting it as a UTF-8 character that marches across. So maybe that's where we start, because we do want to, from the beginning, support UTF-8. Once we got UTF-8 support, then downgrading to ASCII and Latin 1 encoding is trivial, but UTF-8 is the hard one, so we should start with that. So I guess that argues for me to write that piece. So we have a text buffer, yes? Easy peasy. Read a file, copy text, or reference text that we don't take ownership of. What are we calling this chunk of text? So usually it's a file name. It doesn't have to be. What are the contents and how big is it in bytes? Now we want a way to march through this with a UTF-8 string. Do we just look at what I did before? How often do I want to do that? We can. It's not that bad. But first, we get a short restroom break. And then we'll start working through UTF-8 standards for fun and for profit. Do I have in the other project? I don't want to like copy things out of here, but I thought I had a link to somewhere here. No, I do not. Okay, UTF-8 standard. Let me see if I can share a link out. I gotta find the one I prefer. This is not the one I want. This is not the one I want. Oddly enough, I think the one I actually like is this one. Let me see. Is this the one? No. I've got it somewhere in my notes. Hold on a second. I could swear there was a link in one of these files. Yeah, I don't see it. Did I put it in a different object? Huh. Okay, I do not have that particular resource noted anywhere. Well, shoot. Can I find the link I want? Where's that resource? Is this it? I think this is the one. Okay, we'll put it in the thing. Boom. Okay. Now I know this is linked to the ASCII, but let me just share my browser here. I have to trick OBS into letting me share the browser. There it is. Now I can put the browser back where it belongs and pop over. Okay, ASCII chart. Let's talk about character encodings. Back in the day, you had an old teletype with a 7-bit punch tape, meaning each row on the tape would accept up to 7 holes. And a reader on the other side would try to put a feeler through each of the holes, and the ones that went through would lose contact, and the ones that were blocked by paper were left close contact, right? And then it would know what the number was given 7 bits. And that was the encoding that the world mostly went with. It's not the only one. NFAState is another encoding if you're interested in old school stuff. The numbers are different. Let's see, does Wikipedia have a... Yeah. So A through Z started at 8.1 hex, right? But it was a lot of empty space though. Anyway, so this is EBCDIC ASCII 1. So we have a 7-bit ASCII, meaning everything up to this tilde and 127, which I'll talk about in a second, are what are standard ASCII, 7-bit ASCII. There was, at the time also, very quickly, what was called IBM ASCII or extended ASCII, where people would fill up that 8th bit with whatever they felt like, right? So then you started having code pages to say, well, whose extended ASCII table am I looking at? And it just became a big mess. Horrible mess. Terrible. But 127 is the delete key. So if you're typing along on your teletype and the person on the other end is receiving stuff, if you made a mistake, you would hit the delete key, and what it would do is it would punch all 7 holes. And they'd all be all open contact, and it would say, oh, this character should be ignored and move on to the next one. So that's why 127 is delete, in case you're wondering. These are some control characters. 0 is used as a special end of string character, the null character. Some other control characters. Space is at 32, right? So ASCII won the war over EBCDIC and whatever else was out there. So when they decided to build something better than all these code tables, you had to look up which code table you're using to find the right extended ASCII to use. And then if you were doing like more complicated stuff where you'd actually be running multiple code tables at the same time, this became a big mess, right? So they came up with a Unicode standard, which said we're going to make big numbers instead of just 1 byte of data, or in this case 7 bits of data. We're going to run huge amounts, and we call that ASCII. Now ASCII is just a number, or Unicode. Unicode is just a number per letter, and they decided, well, for all these letters, we're just going to use ASCII. So if we hit anything in this range, it's 1 byte, and we're done. But when we go to, there are different ways to encode Unicode, and the most popular right now is UTF-8. So in UTF-8, if it starts with a 0 bit, that means it's a 7-bit number, and it's just in this range. When we go to 2-byte numbers, it gets more complicated. Right? So here's the original ASCII, 127. We ignore 128 through 255. They are no longer valid characters at all in Unicode, or in UTF-8. And then we have to signal to the user, in the first byte of our character, how many bytes is this going to take us to represent? Okay? So if you want, Greek letters or Cyrillic letters or a lot of these other Latin variants, right? Mathematical operators. Yeah. So here's our Greek letters, right? Here's our Russian, the Cyrillic alphabet. If you want any of these, we need 2 bytes to represent those. And if you want to represent 2 bytes, it's going to be a special byte pattern in that first byte. They'll tell us this is a 2-byte pattern. If you want a 3-byte pattern, now we're getting into some whoa. Now we're getting into some what? Arabic. What's the computer doing? My mouse is unresponsive. I unplug. Click start working. I just overload it with how many characters on this page. Yeah, so you got your katakana, your hiragana, braille characters, astrology symbols, there you go. Roman numerals. They have a special pattern in their first byte to tell you this is a 3-byte character. We're going to turn UTF-8 into Unicode. And then the 4-byte, same thing. Okay? So, what we need is to hide the browser and just get started on that. Or if there are questions, let me know. But yes, that ASCII link I sent out is the one I usually go to for simplicity. So this. We don't need. Oh, text buffer's fine. VV source. So we want a UTF-8 character reference header. Okay. Unit 32T value. So this is the code point, the Unicode value. We need this needs to talk to a text buffer, because that's what we're going to walk over. So we need this character starts at m_byte offset, a byte size for the character, and then we need a character offset. Is that it? So look at our compiler for let's take a look. So this is our code point byte count, character offset, for byte offset, byte size, character offset. Okay. Then we have the buffer that we want to talk about. So const text buffer star. What buffer are we talking about? And we want to know, is this valid? Is this a valid character? Because there are a lot of ways the character can go wrong, including you never set a buffer. Okay, so let's implement some of this. UTF-8 character reference. Oops. CPP. Let's see. Okay. So by default, our code point will be 0. Our byte size will be 0. Our character size, character offset, 0. Our set will be 0. Our buffer will be null. And is valid will be false. That's basically it. Clear. Seems like a useful function from time to time. Let's do that real quick. It's basically this. Okay. We do want to be able to ask, is valid? That is an important thing to know. We can do a couple of other things from here. We do want, so the reason we're doing it this way is I'm not going to ever create a copy of a string once we've read in the file, unless we're logging. I don't want to do a lot of string copies. I don't want to do any of that. So we will also eventually build up a UTF-8 string reference, which will be similar to this, except it will have a character length as well. And yeah, some other things. That's fine. Okay. So it is valid. Turn is valid. We want to be able to have the old copy constructor, const UTF-8 character reference and other. We want to assign this. Those will be useful tools. So we'll just do a copy of everything else. Assignment. Which is a simple copy. Okay. And last but not least, we want to create a UTF-8 character reference given a text buffer and an optional byte offset. This is kind of where the real meat and potatoes starts to come together. I guess we need an insert. Oh, do we need an insert? Maybe insert's not the right answer. Buffer's not equal to null pointer. We do useful things. We could simplify a lot of this stuff. Just like this. Clear. Contents of this equals other. Return concept of this. We've got to do that. So that's actually a nice little bit of simplification. Okay. However, if it is, then m underscore, we're not going to do that yet. M underscore buffer equals buff. M underscore byte offset equals byte offset. Now, code point byte size. Oh, character offset. Well, we don't want to do that. We don't want to start from an arbitrary point undecided. Oh, great. Not for now. Let's go char offset equals 0 because we're at the start of the buffer. We're at byte offset of 0. And we'll only know if we're valid if we pass through everything else. So we need to compute byte size, code point, and that's it. So we're going to make an update function, which will be mostly a void update. Let's see why we do it this way in just a second. Blah, blah, blah. We will not know the byte size. We have a byte offset. We don't need to worry about the character offset or the buffer. Okay, so m_buffer buffer at byte offset is the byte we're going to look at. So we're going to start at the very first character and if character starts with a 0, so 0x80 equals 0, so I don't know if people want me to walk through the bitwise comparison here. We're basically saying, is the top bit 1, C and top bit equals 0, then m_byte size 1. Let's see, character and, so here's the thing, signal a 2-byte character. We're looking for a specific pattern. We're just going to fill this in for now, equals 0x. So what I'm looking for is a 1 and a 1 and a 0, and then whatever we want. So that's going to be 8 plus 4 and this and 2. So this is the value we're looking for. So 8 plus 4 is 12. 12 is C. So if C and if the character and these 3 bits equals C0. C plus 2 more DE. So here's the thing. Mask that we want to check for is 1110 000. That's the mask we want in binary. And the value we're looking for in binary is this. So when we AND our character with E, which is this, we want to get this, which is C. Okay? Does that make sense? Byte size equals 2. Maybe we should be consistent and also mask out the first one. So we only care about the first bit, so that's the mask. And we want 0. Okay? Is this all clear as mud? Awesome. Next one is a little trickier. Well, it's not that much trickier. same as this one, except we want one more. One more. We're going to check the first 4 bits, and we want to get the pattern 1, 1, 0. So 4 bits is F. That's going to equal E, right? Byte size equals 3. Let's hit C, and okay, and this is where it gets actually even more fun. It's just this thing. So let's just copy this. Except we're looking for yet another one here and another one here. So the answer will be F. But we need to check F and 8. That will give us a 4 byte size. As far as I know, nothing goes above 4 bytes, but the UTF-8 standard has that room. It can keep growing more bytes. So far, we don't need it. Turns out that 4 bytes is quite a lot. Well, I was going to add the link to my code, so I stopped looking for it. Design 215 toolbox. Okay. Now, once we have the byte size figured out, else byte size equals 0. Okay, so we're always going to get a byte size. Now we need the code point. So one byte, 2 byte, 3 byte. So a switch table can be very fast in certain circumstances. This may be one of them. Case 1, case 2, case 3, case 4. If it's 1, then our code point or our value or whatever just equals the C. Nothing to do. Super fast, super easy. We don't even need that. We'll be fine. Otherwise, the code point is going to equal 2 C stored with this thing bit shifted 8. Backwards. C bit shifted 8, and then the byte following it. That's the 2 byte. 3 byte. We bit shift the C 16. Or that with this thing bit shifted by 8. Word with the next thing plus 2. No, we could be. Maybe we could be even more clever. Can't we? That's fine. That's fine. Let's not overthink it. Case 4, the code point, shift 24. That's the wrong direction of shift. What on earth are we doing here? Can't type anything. 16. This thing gets shifted 8. 4. Plus 3. We only need to. Yeah, we don't need to modify that. Otherwise, by default, code point equals 0. And I think that's it. How many bytes? What's my. This is not my code point. Code point is the code value. We should not call this code point. It's our UTF-8 value. UTF-8 value. Although even this isn't quite good enough. I'll tell you why. Because we don't actually know if it's valid yet. This is close, but it's not quite right. And I'll tell you why. Where's the standard? Standard. This is standard 2 bytes. Okay, so where's the. Let's turn on the old browser for you folks. Okay. So here's our C0, right, that we're looking for. Byte 2 must start with 1, 0. So the 1, 0 prefix means this is a continuation byte, meaning this is not the start of a letter. This is a byte in the middle of a letter. Does that make sense? It's the reason why. Let's see here. Let's hide the old browser again. Oh no! Come on. Who stole my mouse? Okay. Turn off the browser. Okay. It's the reason why instead of going from 1, 0, looking for 0 to looking for 1, 0, it's because 1, 0 means this is a continuation byte. So, what's my code? Sharp B1, B2, B3, B4. We'll just reuse these over and over again. That's fine. B1 equals that. The other thing we have to ask will come along shortly. If B1 and we need to check 2 bits. So that will be 8 plus 4 is C. If those 2 bits are 1, 0, 0B, 1, 1, 2, 3, 4, 5, 6. Value 0B, 1, 0, then we don't care about the rest. So I hope that these are the ones we care about. So that's why this pattern does not show up above in here. Special 2 bits to indicate we are good to go. Don't want to clear. We want to do something similar to a clear. Go to invalid char. Okay. Byte 1 and byte 2. This actually simplifies quite a lot. We can round to it. Or this would be byte 1 if it shifted 8, and then byte 2. Byte 1 passes, and byte 2 passes. E3 and 0 x 0 equals 0 x 0. Four, 16, 8, or the last one. One thing we may want to do is a reason why. So maybe we don't have a valid prefix. Maybe we had an invalid continuation code, continuation byte. Byte offset and character offset do not get changed. Buffers that get changed. So I think we do need to add that UTF-HRF source. I want an enum class invalid reason. So we will have uninitialized end of buffer. We will have invalid first byte, invalid continuation of byte. Invalid reason, valid reason. Invalid reason. Now we can always ask, why is this character invalid? Okay. Which means this thing needs to get copied everywhere. Update will fix that one. Equals other dot same. Clear. Invalid reason equals HR invalid reason of uninitialized. That's enough good reason. Okay. Else _, invalid reason equals UTF-HRF invalid reason uninitialized. Invalid first byte. Here, invalid reason. Oops. Go to invalid character. This is basically the same everywhere. These three are invalid continuation bytes. Okay, a couple more things to check. One, are we at the end of the buffer? Or, oh, we have an incomplete character. Those are two more. Okay, so end of buffer is easy to check. We check that way up here. If m underscore above byte offset is greater than or equal to buffer m underscore buffer. I think it's called size. Text buffer size, yes. End of buffer. Okay, one more thing. If m_byte offset plus m_byte size greater than or equal to m_buffer size. But this will be an incomplete character. Meaning we got a valid byte or two, but we needed more bytes off the end of the buffer that don't exist. Whew, I think that's all the error cases. Now, we start with UTF-8 because, one, we want to support UTF-8 out the gate, and we will generate simpler code for ASCII and Latin 1 encodings later, because there are simplifications on this. Well, because UTF-8 is a superset of UTF-8, of ASCII. So simplifying is easier once we've built complexity in. Two, every time you walk through a UTF-8 buffer, you are required to report basically all the errors like this. We can't be soft and ignore and say, hey, this continuation byte doesn't look right. Like, that's just not going to fly. This is not going to work. So, when we update the character, we have to do all these checks. Are we at the end of the buffer? Like, we're already passed. Then we can get a character, ask how many bytes. If we don't have a valid prefix number of bits, invalid first byte, bounce out. If where we are plus where we have to end up is bigger than the buffer, bounce out for incomplete character. Can we extract a reasonable value? That has to pass the continuation byte checks. And then hold on. We got here. There is never else here. Byte size equals 0. We can do that. Could start with the default one here. That's let's just put it in the else. Go to invalid. So, if and only if all of this is correct, do we get a valid character? I guess we add valid. Or none. There is no invalid reason. Which we can set at the top of this function. Okay. Whew, we're getting close. UTF-8. Now, there are further elements of the UTF-8 standard that we're just going to ignore. Like, we're working on byte correctness. If I remember right, there are actually whole dead zones in the UTF-8 standard where the characters are otherwise valid but considered invalid because they're in a special range. I don't remember what those are. Let's see. So in a 2-byte character, there are 2048 possible ones. There are 1,888 out of that 2048 that are valid. So I don't know where the invalid ranges are specified in this web page. Maybe I have to go to an official standard. But again, do I care? Kind of not at this point. So, we're not going to waste too much time about those dead zones. UTF-8, here we come. Okay, so we can initialize our character reference, which is going to point inside a buffer. Here's a buffer, here's our character offset, byte offset. Are we valid? The last thing we need is to be able to advance our character. I need a function that moves us forward. So we need a void advance. What we do is we say, oh goodness. If m underscore is valid, the easy thing is m underscore bytes offset plus equals m underscore byte size m underscore char offset plus plus. And then update. So we go figure out our first byte, number of bytes, etc., from here. If it isn't valid, we can try to squeak past it and continue just in case. But it depends, right? So if we are past the end of the buffer, this is kind of where that invalid reason comes from, right? M underscore invalid reason. Why are we invalid? Because each one might have a different mitigation. Is that true? Think about that. While we think about that case, UTF-8 ref invalid reason done. Yeah, okay, that did not work out at all like I wanted. Had a goofy keystroke in there. Okay. Report that. Case UTF-8 char ref invalid reason. There we go. So here are all the options. If the valid character is not invalid while being invalid, that is a So inverted my logic here. That's fine. This shouldn't be possible. Log note error, or like this is a program error, not a you said that's a bad text error. UTF-8 char ref dot advance. How can we be invalid? Not have a reason. Okay, good, helpful message. Uninitialized. Yeah, if you call advance, we just don't do anything if it's not an initialized character, right? That's fine. End of buffer, we don't do anything. We advance, we do nothing. That's fine. It'll just stay at the end of the buffer. If the first byte is invalid, then we advance one byte and hope we can recover. And we don't update our character offset because this wasn't a valid character. Invalid continuation byte. think we do that. If the character is incomplete, then we can't do anything. We're already past the end of the file. Does that make sense? So really, there's only two possible. There are two normal. Like these two are normal. Like I don't care if they're non-initialized. We just don't do anything. And I don't care if we're at the end of the buffer. Just don't do anything. We don't advance past the end of the buffer. This might be recoverable. This might be recoverable. Incomplete character. Again, nothing there to do. We should never see that message ever. Is that it? Okay, last thing. Return. One more piece I want. Static const star array of invalid reason names. Equals an array of strings which we can turn into strings. Char star invalid reason string. Return underscore invalid reason. Return UTF-HRF invalid reason names of go ahead and hard code these. I never trust anybody's auto-generated stuff unless I'm 99% sure it does basically this, but I always feel better if I can look at it. That way, though, if we get an invalid character, we can easily see in human readable terms what it is. And done. Okay. In theory, we can use this to move all the way to the end of the text buffer. So let's add it to our makefile. UTF-8 character reference. UTF-8 char text buffer with this. Compile, clean, and debug, and see how many typos and how many semicolons we forgot. Oh, yeah. C standard int Q. Oh, yeah. Our constructor, I forgot to remove the colon. Is valid. Small typo. Properly scope things. Just grinding away here. Yes. Once we get through this, yes, I did expect that bracket to be closed for some reason. Suggests parentheses. Yeah, that's fair. Now it means I have to. Right, search for C ampersand, friend. Search for equals, back, friend. Search for and 0x. Friend. Cannot convert. Oh. Let's just get const char star string equals contents. I don't want to type that out over and over again. String. So everywhere here. Underscore buffer with S. Okay. We got semicolon. Jump to label from here. Process initialization of character C. Really? It wants me to declare all the variables before the first jump. Okay. Okay. Oh, bots in the chat. Gotta love to see it. Oh, let's. Oh, perfect. Good. One warning: unused variable byte 4. That's fine because B0 is C. do we give ourselves more descriptive names at this point? SC byte 1, byte 2. Now, at the very least, we should change C to B0. 1, 2, not that one. Yes, yes. No, 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 no. I think that's it. That's all we needed. Oh no, we need C. What, 0, 0. Zero. All right. No warnings. Okay. So we know, well, we should test it. We should test it. We need to walk over a file. So let's get a test.text. Stupid bot. Agreed. Let's not make a whole file. Let's just go to main. Not include UTF-8 char. Yeah. We're gonna do all this stuff, but then we're gonna get a text buffer test. We will want to reference the text. So const char test string equals hello world. Oh, who writes grammar like that? And then, how are you on this gaming adventure today? Not gaming today. Today is compilers from scratch. We were working on a UTF-8 string processing. So I actually need some different letters. Let's see here. What is let me get some example texts here. From English to gosh, so many languages. Russian. Let's see. Let's do bread, which is clear. Bread. I did know eggs once. It's yitsu, right? Eggs or egg. Yitsu. And apple. What was apple? Yarmulke. That was it. Yarmulke. And let's do something Greek, I guess. Let's go Greek. Bread, egg, copy, paste. Boom. Okay, so we have some English, we got some Russian, we got some Greek. I don't know any of those letters or what they sound like, but that's okay. Our test buffer dot reference this test string. I need to give it a label. Test. Give it a test string. There we go. Okay, so we have a test buffer. log node test text. Make sure we're getting what we think we're getting. Boom. UTF-8 character reference C given the test buffer. Oof, okay, how are we doing? Hey Brian, welcome back. How's it going? Today is variety day. We're doing compilers. Specifically, we are building a UTF-8 character reference that will help us walk through a text buffer in UTF-8. So we'll see how that works. So there's our character. This is a number of characters and a number of bytes. We could pre-compute number of characters and bytes mentally, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bytes. 14, 16, 18, 20, 22, 24, 25, 26, 27, 28, 29, 30, 32, 34, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 4, 6, 8, 60, 62, 4, 6, 8, 70, 72, 4, 6. Int expected byte when equals, what did I say, 76? Int strlen len equals strlen test string. We don't really have a lot of ways to look at the things in the character, so let's just make some changes to that real quick. Let's make everything something we can look at. Nothing is private now. It's all public. Character length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51. Expected char length equals 51. Strlen byte len hit text buffer then test buffer dot size. I just want to make sure that like everything is working the way I expect. I manually counted 76. Strlen should return the number of bytes. The text buffer should return the number of bytes. So all three of these should be the same. And we expect 51 characters. While C is valid C.advance. Kind of want one more thing out of C. Let's go in here. I want see, advance is valid. I want const char star to C string. I want to be able to see it as we go. So if anybody has any questions about UTF-8 or whatever, just let me know. Happy to walk through it at just about any level of detail within reason. If underscore is valid, char star result. Result equals the char array of m underscore byte size plus 1. Else result equals new char array of 1. And result 0 equals the null character. Boom. Third copy. Underscore buffer. Into contents. Stir in copy. Plus underscore byte offset. Into result. And the n is underscore byte. I think that'll work. Sorry, but now I'll do a big stupid question that probably I already should know the answer. In the true compile part, will you compile in what? Question mark, will it translate the code in assembly? Unclear what section of code you're talking about. I'm not clear yet. True. And this is valid? The part that converts the text in machine language. Oh, text in machine language. Oh, gosh. Okay. So what we're doing is we're saying in assembly language, I need room on the stack to store a pointer, and we'll treat it as a character pointer. The computer itself does not care that it's a character, only that it's a pointer. This character pointer is only useful to the compiler, not to the computer. Then if we say, and we're going to say set it to 0. If some condition is true, we want that pointer to be a new chunk of memory. So we're going to say, so what happens is when we say new, we say, hey, operating system, give me some memory. I need this much. So it's basically character, the size of a character times the number of elements I ask for. And it's going to give me back a chunk of memory. It's going to say, here's the address. We're going to store that in results. So this is right now give me some memory on the stack, set it to 0. If things are true, we're going to make a system call, or maybe it's a library call. I don't care which. I'm going to ask someone for some memory, and it's going to set to a new address. So I'll have a place to write data. So I'm going to say, hey, buffer, tell me where your context is. That's an address, a pointer. And I'm going to add some number of bytes after that. I'm going to say, tell me where your text starts, and I'm going to jump to here. Then we're going to copy from this location this many bytes into this newly allocated buffer. You have to add +1 to the number of bytes so that this will put as a null terminated character at the end. Otherwise, we get a new character array of 0 string length, and we say the first character is the end of string character. Return. Does that make sense? I don't know if that is at the level you want it answered, so if not, let me know. Stir end copy is a library call, so the machine code generated would probably not be recognizable. They always want to optimize the system calls or the library calls to such a degree that you probably wouldn't be able to look at it and be like, oh, I can tell what this is doing. Okay, all right, cool. If that's the case, then we'll go into main, and what we want to do is log a bunch of stuff about each character that we come to. UTF-8 test. We want to know which character this is. We want to know what character it is. We want to know its offset and its byte length. And honestly, that's probably good enough for now. So C dot M underscore char offset C dot post char star temp equals C dot 2 C string. We will have to delete that later. Not logging it. C dot M underscore byte offset C dot underscore M underscore byte size. I think that's enough information. So we should see like all of these things be what we would expect. Expected modulus D equals modulus D equals modulus D bytes. So the expected byte length, stirlen byte length, and the text buffer byte length, those should all be the same. And that should C actual, or let's see here, actual byte length equals C dot M underscore byte offset. So the last character should put the byte offset at the end of the text buffer, which is the same thing as the size of the text buffer. C actual. And then note expected modulus D equals modulus D characters will be expected char lane and character dot actual char. We'll see dot M underscore char offset. Okay, whew. Let's make sure this is working. Probably understand better on future episodes. Oops, not by count. byte size. Oh. There we go. Wants this to have a semicolon, that makes sense. Kitten is not a data type. They are entirely correct. I agree with my compiler this time. Where are we at? Up, VB. Build completed, so we should be able to do / source build debug. Okay. Something's clearly wrong. Kill it. Okay. I don't get it. While character is valid, do things, then advance. If that advance ends up with us being invalid, it should hit here and bounce out. Oh, what was I thinking? Should have not inverted that logic. Warnings. What? We'll char that. There we go. That's better. New shell. / source. Builds debug. Okay. We have problems already, and that's fine. The 0th character was null, had a character of 1, a byte size of 0. And then it blew up because we kept going. Except it shouldn't go in here unless it is valid. Oh, okay. 10. There we go. That should help. Hey! Super close. 76, 77, 77, 76, 51, 50. I can believe off by 1 errors. H. E. Don't like the fact that these strings are not 0 terminated. Do I have to 0 terminate myself in a stir n copy? That's entirely possible. Stir n copy. Result sub m underscore byte size equals okay. So where are we at? HELLO world. These are all 1 byte characters. They'll advance by 1. X. Well, clear. 2 byte characters followed by a comma and a space, which are 1 byte characters. Yutsu. 2 byte. And then Yamaka. Period space. You get into the Greek characters. Space 2, 2, 2, 2, 1. Now, I'm willing to accept that this 76 here is me miscounting by 1 somewhere. Oh, no, wait a second. 77, 77. I can believe that the actuals are 1 less than what's recorded. Except there's no period. Where did the period go at the end of my string? So in here, I expect a period at the end of the Greek. I'm not getting it. So text buffer might be lying to me. Yeah, so it's not getting that. I expect 51 characters. And I only get 50. And we did not get the period at the end. I would expect this last number to be 50 dot period 76 comma 1. Okay, so that's this one. That is unfortunate. This one, number of bytes. Honestly, the byte count looks fine. Strlen and text buffer len are the same. Those are 77. Did I math wrong when I counted the bytes? Oh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25, 26. 26 2-byte characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14. 15, 16, 17, 18, 19, 20, 22, 23, 24, 25. $77. So I just counted wrong. We do expect 77. Look at that. If I count right, it all works out. No, so if you're gonna understand UTF-8, now is the time. So let's just take a quick look because we're getting some incorrect data anyways. Let's take a look at what we're getting now that I've counted the bytes right. 77 was what we manually counted. 77 is the Strlen number of bytes, which is correct. And text buffer figured out that it was 77. But we only scanned forward 76 bytes. Okay, which means we also didn't get all the characters. They're supposed to be period at the end. So if we go to UTF-8 character reference, what we're doing is we're taking a text buffer. And we're saying we're not gonna copy text out of the text buffer, we're just gonna keep track of where it is in the text buffer. So here's a pointer to the buffer, and we're gonna start at byte 0, character 0, and then we go to this update function. When we advance our character through the buffer, we say if it's valid, move forward some number of bytes, add 1 to our number of characters, and then update our values. Otherwise, if things are wrong, blah, 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 not interesting. meat and potatoes is here. UTF-8, there's a lot of ways to go wrong. So we check those. We set up some initial values. Then we say, hey, if our byte is greater than what happens if it's equal to? If byte offset is 77. Anyways, that basically means we're at the end of the buffer, right? If where we say this character starts is after the buffer, then that's invalid. If it is valid, then we can ask ourselves, is this a 1-byte UTF-8 character? Is it a 2-byte UTF character? Is it a 3-byte UTF character? And is it a 4-byte UTF character? Those are the options currently supported. If not one of those patterns, then it's invalid. Okay? Then, if where we are plus how big we are is bigger than the number of bytes allowed, then that's invalid. It means that we've only got a few of the bytes we need, and then we hit the end of the buffer. So that's an incomplete character at the end. If that's all fine, then we can say, all right, in the case of byte 1, we know the value. We're done. M_, invalid reason. Pretty sure we set that at the top. Yeah, okay. So we just copy the byte, we're done. However, if it's not, then we have to get the next byte and make sure that it's a continuation byte, properly marked with the first 2 bits. If that's true, copy the 2 bytes into our value, and we're done. Otherwise, it's an invalid continuation byte. Same thing if it's a 3-byte, we'd have to check both of the characters after the first byte, and the 4th byte one, we check all 3 bytes after the first one. And if all of that is correct, then we can return. Otherwise, we don't have a valid UTF-8 value, we don't have a real byte size, and this character is not a valid character. And that's basically UTF-8 in a nutshell. The best viewers have arrived. Neg Vorsa, welcome, welcome. So that's basically UTF-8. We're trying to walk over it, but we're ending 1 byte short. So let me think about 2 places where we check buffer size, and we use greater than equal to in both cases. You know what we could do? Actual byte length should be the byte offset because we walked off the end. So let's take a look. Log root ended c dot invalid reason string. Just see if it's end of buffer like I think it is. Maybe that's my problem. So if the best viewers are here, incomplete character. Oh, odd. Oh, I know. I know what's going on. So who are the best viewers? I like viewers that helped me. Yesterday, I had one that actually knew quite a lot about OpenGL and port audio. Very helpful. Neg Vorsa, yes, you've been here before. Well, hopefully everybody's having fun learning UTF-8. Okay, I know what the problem is. Here, we have to ask if we're past the end of the buffer. But here, we have to make sure that that is true. So if we're at byte 76, and we have 1 byte to add, that puts us at 77, so it's only invalid if the next character, not the current character, goes off past the end of the buffer. Boom, done. Now it's going to work. We're going to get all 55 characters and all the bytes. 77 bytes. 51 characters. Passed. Okay, so we now have a way to walk through UTF-8 text buffers. It always bothered me that we didn't have support for UTF-8. The ones already watching, of course. That's true. You know, the best viewers are the ones that are watching. It always bothered me that regular expressions didn't properly support any UTF-8 in any meaningful capacity. I've been bitten so many times by somebody copy-pasting something on a web page and getting non-breaking spaces. And then my regular expressions don't work. Makes me sad. Okay. I'm gonna say let's go to the journal. Journal, we should write what we did. We need UTF-8 walk through text buffer. I'm gonna call that done. Initial implementation of UTF-8 char reference. It's done and tested in main. We're not testing every possible error case. Do you have wide characters? Okay, let's see here. Where are we at? For UTF-8, after validating the size, I think there's an extra step that must be done to validate the ranges. Yes, we are ignoring ranges. We are validating correct bit patterns only. To validate the size, we validate the continuation bytes, continuation bits. We are not checking invalid ranges. I wonder if I can pull that up really quick. Invalid ranges. Not character ranges. I want the Oh, those are some groceries. Groceries. I don't see any groceries. Do you have wide characters? No, we are not doing wide characters. Wide characters are not what we were looking for. If I remember right, wide characters was Microsoft's attempt to make a 16-bit character, 16-bit fixed width character. Yeah, basically UTF-8 beat it out. The text in Russian is bread, egg, and apple. Yes, good work. Oh, groceries. Yes, you are correct. Those are some of the few words in Russian that I still remember when I was kind of looking into it. Хлеб, яйцо, and яблоко, which are probably pronounced horribly, especially now. But then I just ran it all through Google Translate for the Greek as well. It's also bread, egg, and apple. So we have UTF-8 support. Let's get that committed while we can. Git status. Git add everything. Journal to do make file project. We made some up. Oh, we should add that to the journal. Tokenizer definition prints rules nicely in a table. That was another thing we did earlier in this warm-up. Tokenizer definition prints in a nice table. UTF-8 support has arrived. The reason we start with UTF-8 is we can always downgrade to Russian and Greek are both 2-byte characters. If we wanted to, maybe we should do that. Let's do let's add one for this. Let's go ahead and extend our test. these should be 3-byte characters. And I'm not even going to guess at this number here. But we can count how many more characters we've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more characters? Should be 61 characters. If that's the case, we could probably work out 1, 2, 3, 4, 5, 6, 7, 8. 8 times 3 is 24, 25 more, plus 25. Japanese characters should be 3-byte characters, just to stress our system a little more. 100 and again, I probably make mistakes. 61 characters, so I probably didn't count the period at the end. Yeah, we have 3-byte characters, and those all look right. Oh, I forgot the space, didn't I? So 1, 2, 3, 4, 5, 6, 7, 8, 24, 25, 26, because there's a space and a period. That's where the error came in. There we go. Do we want to do Chinese as well? Russian character UTF 2 bytes. Yep. You want to try Chinese? Traditional. Heck yeah. Don't even ask me to think about pronouncing this. I believe kanji are 4 bytes each. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh wait, no, what am I saying? 1, 2, 3, 4, 5, 6, 7, 8 times 4 is 32, 33, and the space is 34. 34 more bytes. And it's any the character count update. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more characters. Russian character. Yep, Russian characters are 2 bytes. Greek characters are 2 bytes. Japanese are 3 bytes for katakana hiragana. And I think kanji. Oh. So apparently these Chinese characters are 3 bytes. That wasn't what I was expecting, but it's fine. Maybe we look up something in the 4-byte sample that looks interesting. I've always liked the, what is it, dominoes? They have like cuneiform Egyptian hieroglyphs. We could go for some Egyptian hieroglyphs. What else have we got? Musical symbols. Let's do musical symbols. Let's take the Chinese out. It's not a 4-byte thing. Go back to 61. Take out that. Let's just do some. Oh wow, okay, that's not supported by Emacs or by my font. Dominoes, maybe it'll take dominoes. Where's a double 6? Double 5. I'll just take dominoes. Okay. No. Lost my dominoes. Where's double 6 horizontal? We can go with a vertical blank and double 6 vertical. So that should be 1, 2, 3, 4 times 4, 16, 17, 18. instead of 61 characters. 1, 2, 3, 4, 5, 6. So 67 characters. That should get us our 4 bytes characters. $121, 67, very nice. Okay, that's pretty good test. Does this mean the font has no glyph for those symbols? Yes. It means my font does not support all of Unicode, which is not surprising. I think you have to be a pretty widely used font to get that kind of support. This is a programmer monolith font called Anonymous Pro. Let's see. Here we go. I'll throw a link. It was pretty specifically designed for programmers to make sure that each character looks different and unique. So like number 1 and lowercase l don't look alike, O and 0 don't look alike. But yeah, I don't expect it to support the full glyph sequence. I'm actually a little surprised that they got dominoes in there. But that's just kind of the way it works. So if other people have their favorite programming font, let me know. But I've been very comfortable with Anonymous Pro for like 15 years now. I got this pretty early in my career and just kind of copy the file around with me. Okay, good testing. Git add everything. Git commit -m. Commit -- amend -- no edit. There we go. Okay, over to the journal. Now that we have a way to walk through a string as a UTF-8 buffer, we can now walk through the pattern to build our NFA. Where are we at? 3:30. It's about time for my snack. Let's go to main. Now that we've tested it, I'm going to delete it. Git will keep this forever. That'll be wonderful. And that means we no longer need this. What we're going to stub out real quick is, so the old code that I wrote years ago, or yeah, it was a while ago, called it an NFA compiler. We could call it something else, but NFA compiler is not bad. Or maybe like pattern to NFA converter. Since we're working on a compiler, overusing the word compiler to mean slightly different things is not great. So pattern to NFA converter, interpreter, converter, converter or translator. This doesn't actually change the pattern at all. In fact, the pattern remains completely static. This is probably good. Here's the old one. Compile. We don't have to worry about merge for a while. Init. Set roots, add state, scan pattern. This is why we needed the UTF-8 character. It's for walking through the pattern. Reduce, reduce, patch. Okay. Okay, so we're gonna. We'll probably need a clear function. It doesn't have anything to start with. I built this before as a purely static thing. I don't think we want to do that. In the future, we will want to multi-thread our text to NFA. Oh wait, what am I saying? This is not something that we're shipping out. This is part of the tool itself. So being static is fine. Just being pure static, I'm okay with that. Static, we will use the same names for NFA. File int rule ID, token ID, const char star pattern, NFA star and NFA. I don't remember why we pass one in and take one out. Okay, Tokenizer Generator. NFA compiler. Compile. So I guess it will either accept an NFA pointer a. I don't actually remember. Why we pass one in and return one. That would be useful information. We clear an NFA if it's passed to us. We initialize it. Why are we returning it? I don't think anybody actually uses that. Yeah, it's returning it, but I don't know why. Yeah, there's no reason for us to return it. Okay. Void? Maybe we return Boolean for is valid or something. Put NFA. Okay. Is the project public on GitHub? No, it is not public on GitHub. The only things I have put on GitHub are small studies that don't contribute to large, complicated projects at all. So, like, I have a random number generator series in there that is different number generation methods and different things you can do with them. But I don't want to feed the AI anymore. If it's going to try and replace me by scanning code on GitHub, which is what they all do, I'm not going to participate in that system. I like programming for a living. I don't want a computer to do it for me, so I will not increase their knowledge base. Right now, it just lives on my hard drive. There's no clear. This is a static thing. Okay. So let us pause briefly for a snack run. And then we'll get into the meat and potatoes of things. Be back in a minute. Okay, snacks have been acquired. So we can walk forward through that. Let's see. We need. I mean, honestly, looking back at the other project, there probably isn't much of a better way to organize than what I've got here. We will need a class for that. We will need a class for that. We have a UTF-8 character reference, and we need a text buffer. We will forward declare NFA fragment here, even though it's not necessarily exposed anywhere else. I'm going to skip merge for now. Initialize our NFA. Scan pattern. Those are really the start, and then reducing fragment dealings. Set root. Add state. I remember what NFA contains. NFA has a text buffer. I made those all public, did I? That was very clever of me. Probably for testing, and then I never moved it back out. It's literally just a list of all the states, and here's the root state. NFAState, what does that one look like now? All the different things we can do with a state. This terminal is information, log here, update buffer. Oh, I remember what that's about. So an NFAState has two outs, which I remember. Is it a start state? Will I need to kind of reduce save? Has it been visited? What is our index? Operational names. So some of this just needs to be built and fleshed out. We need an FA, we need an NFAState to put things into. How much of this do we copy? Do you remember that as well? And why we built it that way? So, I'm trying to remember what order I built things in the first time I built this, because there's like a discovery process that went into it of what do I need to know when and where and who needs to know it. I kind of know all that now, except I don't remember how I arrived at all that. So it's not like I can walk through the same process the way that I did the first time, because I have some preset knowledge. need that. We need to initialize ourselves for the run. We will need to scan through the pattern. This. Fragment out. Separate question. Okay. So the whole point of fragment out is we're going to end up with little tiny clouds of partially put together NFA fragments. And then we have to keep track of what the start of that is and what all the things that lead out of it are so that we can make all those links, put all of that into a different fragment as we slowly build those fragments up until they all combine. So in here, let's put information there. We clear the NFA in case there's any data in it from a previous run. And then we initialize it. That makes sense. We need a list of fragments. These are going to be going on and off all the time. Buffer and theme to the fragments. fragments reduce. Okay. I do normalize all of those things. So that's another thing we'll have to remember to talk through in great detail. And then we don't have to return it, so that's fine. Okay, so here's the general flow. If you hand me an NFA, I don't know if it's been cleared or not, so we clear it up. Then we initialize it. We're going to do certain things to it. I don't remember having to do that much there. Know that we want to be that friendly. Okay. I think we will make some changes to the way things work here. NFAState. Let's see. Let's look at the way we did things before. NFAState. This is more of a, for me right now, a decision on how I want to represent it. And not so much the interface. Like this interface is acceptable to me, but I don't think I need to maintain this list of states. I do want a root state, but I want this to be private and only accessible elsewhere. Digital cane buffer. Clear. And clear visited. Well, clear visited is fine. Is it fine? We'll see.
Okay. I used to be here.
Clear. Okay, well, first thing we need, it's an NFAState. We have to have one. I'm fine with operation. We can initialize with an operation. Sense. We can initialize with a character, which makes some assumptions about how this state behaves. Namely that it's a single character match. These are questions we will want questions to ask and answer regularly. We'll talk about what soft and hard accept mean. That's not, as far as I can tell, a standard terminology. It's just what I came up with. Clear visited. Update buffer. I don't want to do that right now.
Not right now. Not new for that. Not right now.
ClusionSet will add later. Use it to add that. Okay. I think we can borrow most of this stuff. I had all of those things public before. Well, it's fine if they're public. I'm going to interact with them a lot in both a read and write capacity. So there's no reason to lock these away. We'll not make them private members. Okay. Am I doing anything in here? So let's see, from the old NFAState we're stealing stuff from. We stole standard int. We're going to comment that one out for now. This we can steal straight up, that's fine. NFAState dot a lot of this we can just copy. So if we get an operation, initialize things in certain ways, there's a start state, rule ID, token X. Easy enough. This is a straight up copy. Set that. While we're building it, we have to be able to ask if building this thing out is done. We check by looking at the possible next states. Can we accept is a tricky question. Is it terminal? Is this a character or any character? That's fine. Clear visited is fine. log. Log is a little bit interesting. Maybe we just steal most of this. Just change what the few things are we need to update buffer. Do we just steal all of this? Just steal all of it. Then we decide what we can remove. Oops, not that one. There we go. Okay. That we're going to change the way it works a little bit. That we're going to change the way it works a little bit. That will change the way it works a little bit. All of that looks the same as what I wanted before. Okay. Log. So when we log, if we've already been visited, do that. Otherwise, we set our visited to true, so we only log this thing once. Inclusion, exclusion, etc., etc. All that looks fine. Update the buffer. I don't know that I want that at all. NFAState. I don't remember what that does yet. Okay. So an NFAState says we want to check one thing. We want to see if the character we're looking at matches this character. Or if the character we're looking at fits inside these collection of characters. Or if this character which we're looking at is outside of this collection of characters. If this is any character, which can mean different things depending on the regular expression engine. For example, a lot of regular expression engines will use the any character operator to match anything that isn't a new line character. Alternate means this is a rule where we have to check left and right, and it has to match one or the other. 0 or 1 is a rule that says the thing underneath me, you need to see, you can either have one or we can skip it. 0 or more means you can have whole bunches of them or none. 1 or more means you have to have at least one, and you can have more, but not necessarily. And then a group operator says, here's a whole bunch of things that I need you to check first before we continue. And a group is comprised of more of these. So those are the operations it can do. So when we pass in a character reference like this, we're saying here's a character to match. Is complete basically says, like, if it's a character, it's complete when we set the character. It's an inclusion or exclusion, similar thing. Any is just basically always complete. Where we ask if it's complete is alternate. There has to be something on the left and on the right to go to. 0 or 1 is only complete if there's a thing underneath it. Same with these. If there's a thing underneath it to check the number of, and to group has to have something in it. So we do need to be able to ask is complete. Can't accept means if we're here and the next character we meet is not something we can build on, is this a safe state to stop it? So if we have, for example, a pattern of like a keyword, right, like import. Well, if we get IMP and then the string ends, well, we can't accept this pattern. This pattern cannot finish because we need to get all the way to T. Now, if T had like a question mark, that means the previous thing, this T, I need either 0 or 1 of them. So if we get all the way here, we can accept. Or if we get after the T, we can accept. Those are the two accepting states for this pattern. Does that make sense? Those are the 2 points where we could accept. If this is like a plus, then we have to at least get past the first T and then as many T's as we want. This will, these are all accepting states. After every T, we can accept. Otherwise, we have to reject and say, no, this is not a valid thing. So, and there's 2 kinds of accepting. One is, does the next character, or can we consume the next character? If not, we're done. So, for example, if we have a pattern that's A through Z plus, that means any character in the range between A and Z, 1 or more of them, we're running the string A, B, C, 1, then this is a soft accept point, right? This is a soft accept point. This is a soft accept point. Meaning, if we get A and something that we can't consume, then we accept here. If we get a B and we can't consume the next character, we can accept there. If we get ABC and we can't consume the next character, we can accept here before this 1. But as soon as we hit that 1, we can't consume any more characters with this pattern. So this is a soft accept point. Here's what I call a hard accept point. Is this character the last allowed character? So in the case again of this pattern, import, after we get T, we're done. We have to accept. There's really nothing else we can do here with this pattern. There's no next checking the next character. This is just the last thing in the word, so it has to be. A more useful case is probably if we did a pattern like quote, anything which is not quote, we don't need that. We don't need the parentheses. Star. So here's a definition for a string. We start with a quote and end with a quote, and anything between that is not a quote. The only place we can accept is after we get this last quote, and we have to stop there, period. There's no confusion, nothing. It's a hard accept. So those are the differences. So then can accept just says, if we can either soft accept or hard accept, then this is an accepting state. Is it terminal? So character, inclusion, exclusion, any are all terminal, meaning we get a character and we're done. We don't have to go into look at the children at all. We just look at it. But alternate 0 or 1 These ones we have to dive into the children, so it's not a terminal element. Do I have to look at the child states? Alternation is our either or. That's a special thing all its own. Can't accept. So can we hard or soft accept? Is complete if we need child elements. Do we have them? Is alternation is that simple. Log, there's our operation. So no matter what you do, the most complicated thing you need to do is check left and right child, right? You do have to know if this is the start state for logging purposes, I guess. Do we? We might not need it. We might. I don't know if it's just for logging. I don't want to prematurely optimize anything out. We have to know what rule generated this NFAState. And if we accept, what is the token that we're going to get? Visited keeps us from looping forever in a number of cases, like logging, or we generate the DFA. We have to check whether we visited this node already. Index. I don't need index. Update buffer. Okay, so we have an NFAState. Copied enough. Those are fine. Conclusions. We will get back to is complete. Can we accept soft and hard? Is this a terminal? Is this an alternation? Oh, so basically is this non-terminal? It's really the answer here. So it's all of the elements that need children, which may be a bad name to consider renaming. This is not is alternation. Maybe is non-terminal. We'll think about that. Clear visited. Yep. So before we log, we clear our visited flag. Again, if anybody has questions about regular expressions or what we're doing, just let me know. Okay. So I keep talking about these clusions. It's a bit of a pun on my part. Let's go to scratch buffer. When we define a pattern, we can, the simplest cases are a letter, a character, right? A literal character. And these are concatenated, meaning if I find an S, A, the next character has to be an S. They have to be concatenated, they have to be next to each other. This is the concatenation operator. Way back in the day, it was actually, you had to put dot in for it to do the concatenation, right? In a lot of early regex pattern matching. So our pattern here would only accept these. But nobody wants to type out the whole alphabet, so if I was trying to say, hey, a variable name is A, B, C, D, E, F, G, H, I, J, K. Okay, so what you would do is you'd say A or B or C or D or E or F, right? For the full alphabet. Nobody wants to write that. So what we have instead is what's called an inclusion range, or a range, or something. Anyways, what you would do is you'd just put it in brackets and say A through Z, capital A through capital Z, meaning anything in between these values is fine. And then we can even add like other things. Maybe we accept a dot of a plus, a minus, an underscore, I don't know, some random characters. Which means that this minus character is special. If we want to include this minus character, it has to be the first character. Now it's minus sign, any letter, an underscore or plus. So this is an inclusion, is what I'm calling it. Sometimes we want something different though. Sometimes we want everything that is not a thing. So I've already done this with strings. A string is a quote followed by anything that is not a quote followed by another quote, right? So this I call an exclusion. And since they're very similar, like anything that is not, maybe we don't want digits, right? We want anything that's not a digit. Maybe we don't want anything between 0 and 9. Or a minus sign. Anything that is not a minus or 0 to 9. Those are an exclusion. So any character that is not in this set is okay. Since they're represented so similarly, I basically have inclusion, which has Boolean, is this include or exclude, right? And then the actual data. So when I talk about inclusions, this is what I'm talking about. It turns out that a single character is itself an inclusion of just that one character. And I choose to do that later for very specific reasons. So when I'm talking about these exclusion sets, this is what I'm talking about. We can include them or exclude them, but ultimately they contain ranges of characters and collections of random characters. Does that make sense? So let's go steal almost everything out of the clusion set. Which is in either or B clusion rule. Okay, it's probably the clusion set contains clusion rules. Go back to the scratch buffer. I'm saying this character inside here is one rule, this minus character is one rule, this range is one rule, this range is one rule, this character is a rule, and this character is a rule. I don't know, maybe rule is the wrong word. It's just a occlusion fragment, occlusion piece. So maybe we rename that. Not sure. Is empty. We can add a character. We can make a range. Value override is a special thing. We may not use that right away. Update buffer. Normalize is one we will want to use a bit. Set operations for different things are useful. I think this was an evaluation of how many characters you could match, and the number of operators we would have to operate to test them all. Let's go look at Clusion rule. We can start with the character. Fine. I really don't remember that. Oh, I remember. Make range. So we can start with the character and then add another character to make it a range. Value override. I don't remember why I put that in there. Let's copy it. We can chop it down to what we need, although we may end up not chopping it much. Source. Clusion rule HPD. I don't remember what value override does or update buffer. I remember everything else. We will want to be able to log this stuff later. I don't know if anybody outside of here needs to know the string length.
Your chips are
Okay. Clusion rule dot CTP BB source usually rule. Okay, paste all this. I know why I did that, but I don't think we need it yet. So we'll leave it for now. To string. String length. I never call it. That's the convention I've been using. TF8 character reference. Byte size. Oh, I made all those public. Yep. So we will need int byte size. Charlen. These are two different things. I suppose we can return the buffer we're working out of. We have questions about valid ready to go. Okay. Yes, we can just implement those real quick. HRF. Advance. There. F8. RF. Byte size. Byte offset. Charland, it doesn't make any sense. Sure. Charlotte is stupid. It's always one character because this is what we represent. Alright, back over to inclusion rule.cpp. We copied byte size. Byte size. To C string. To C string. clearly wasn't paying attention before. If we get this string, we should always delete it. Oh, no. No, I was correct. This is right. I'll tell you why. We get our start string, and if this is not a range, we're just done. We return it. We don't have to do any copy, any printing. Here, we have to tie the two things together in a range. So we need an end and a start string. So that's correct. Otherwise, invalid. Sure. String length. I don't remember. Oh, I better know why. So in the ClusionSet, when we go to write that to a string, we ask all the Clusion rules. What's your result? What's your length? We add them up. And then here we are. Size, if we are range, then we add that number and update buffer. I honestly don't remember what that's for. I mean, do I remember? Not sure. Overlap. We want to be able to ask if Clusion rules overlap each other. That will come in handy later. They're both a range. If only A is a range, we do that. If A is not a range and B is a range, we do that. Otherwise, neither of them are ranges, and we just check. Now, I don't think I have an equal operator. Or greater than less than. So we should fix that. UTF-H rwrap.h. Yeah. This includes things that I don't remember working with. Fact value, unfact value. Big buffer. I do know what those are about. You just steal all these comparison operators. They're dead easy. Except instead of value, I think it's m_value. Yep. Okay, so that's going to help us with our conclusion. We're building. Now we can check all these ranges to see if things overlap. Intersect. So basically, if we have two letters right next to each other, like if I type ABC inside of square brackets, I want it to just say A through C. So this is why we're testing for, do these overlap? Are they intersecting? So that's kind of what we need to do. So if we're both ranges, check the thing. We take two ranges, we put them together, no matter how they overlap, they will still be a range. Take those two together. I don't think that check should ever be possible. Because these are already both defined as ranges. So that shouldn't be possible. If does this use adjacent anywhere? So if A is a range and B is not a range, it's just this. That makes sense. A is not a range and B is a range. I don't think we ever call intersect unless we've already called is there overlap, which means I think we can get rid of all of these checks and just state that by convention. Am I going to regret this? Simplifies things nicely. By convention, must call overlap. Overlap must return true or this method. So basically, we're checking all these ranges to make things actually overlap once. So why am I doing it again here? For smart, we just say if they overlap, do an intersect, which kind of makes sense anyways. Why would you not check first before running intersection? All right, let's just go check. Make file. Let's just add Clusion rule. And just see if it builds. Clusion rule.o. Maybe tokenizer rule with Clusion rule. Do we want to call this something besides Clusion rule? Because it is a rule. It's saying a character has to belong in this or not belong in this. That's a rule, I guess. Condition. Yeah, we'll stick with rule for now. Let's just see. I don't want to make changes to the NFA compiler. Okay, we need to get the value. I guess that makes sense. Which means everywhere in inclusion rule. That's don't need that. Did already take care? Oh. Okay, that should fix a number of things. I don't know. Okay. No declaration. Okay, don't start. If I return it to you, you don't get to lie to me. Invalid conversion tells char star to char star. That was fine. A lot of what we're doing, we really want everything to be as constant as possible, so that it's consistent throughout the run. Except for here. Star temp. Temp. Build equals temp. Star temp. Build equals temp. Yep. guess we leave it. It's useful to the ClusionSet when it's trying to build a string. We'll put it back in. Okay, so that compiled. Now ClusionSet. Start by copying that into our project. Source ClusionSet. We will take a Clusion rule and a UTF-8 reference. Is empty, add character. We're going to remove those value override options again. List of rules. ToString. I don't remember what that does. I do remember what those do. We'll delete efficiency for now, we don't need it. TV source ClusionSet.cpp. Rules are empty. I don't remember why I have to check that. Maybe I don't need it. Oh, no, I do remember why we need it. Okay. Assignment. Add a character. I do not. I can't remember what the override value thing was about. ToString. So for each rule, ask it its length. This is why we needed that. So we know how much to allocate. Front. Then go through each rule and add it to our set. Done. Okay, normalize. What normalize does is it takes each ClusionSet and sorts all of the characters and ranges by the first character. And then, if two things next to each other overlap, this is where that overlap and intersect. Actually, I'm not sure the intersect matters. Skip the first. They're both ranges next to each other. We ask if the characters are adjacent. If the characters are adjacent, we can move them together. So I guess we do need that adjacency feature in UTF-8 character. Also kind of means eventually we'll want the UTF-8 character where everything is protected, not private. We will add the special functionality for this class separately. That's all down the road. Down the road. So I do need to know about the adjacents. So can't ignore it. Yeah, so it's literally just puts it each rule next to the other rule and says, can these be made into one range, or are they overlapped? Are they the same thing? Can we delete one? And it tries to compress everything down as much as it can. Same character, remove the duplicate. And we basically just mark them in a list of things to be deleted so we don't invalidate our generator. Blah, blah, blah. Okay. Then we delete all the ones that don't matter anymore. Intersect.
Oh.
So I have two sets of inclusions. Where do they overlap each other? Which is basically this and this. Onion, yes. Set operations on sets of characters, which may be a single or a range, is fun. And I'm calling it onion. Although really we should just probably should stop goofing around and call it actual union. Oh no, it's a special word. That's right. That's why I had to do it. A union in C, at C++ means something, so I had to call a union operation onion. That's what happened there. Okay. This is a set difference. So all we have to do to create a union is create our new result, push all of the rules from A, push all the rules from B, and then do that normalize step where we put everything in the right order and join all the adjacent bits and overlapping bits and remove the deadwood. So that's all a union is. Even if we have to call it a union, it's now an onion. Difference. Difference is the set difference. So what things are in A that are not in B? So it's like set A minus B. So if I had the numbers like 1, 2, 3, and this one had the number 2, A becomes 1, 3. Well, what it would return is 1, 3. Because the A minus B would leave that alone. And this algorithm, actually the next couple of algorithms are just kind of nasty. If you want to talk through them in detail, let me know. Again, extreme of consciousness things until somebody asks a question. So just let me know if you have any questions. Oh, if print stuff, I see. Where did the print stuff come from? Oh, to pass it in? Okay, I guess. So basically, we're checking all the different ways that we can overlap or not overlap and deciding what to do to combine to take that difference. What are we putting in the final answer? A fully encloses B. So we literally just add the things in A that don't belong in B. And this is the if different stuff nonsense again. Not valid. Discard the difference. Trim A to start after B. Keep the remainder of A. Auto advance. Gold print stuff. Otherwise, not valid A. Manually advance. Like I said, these set operations get very complicated, and it took me a long time to work through them the first time. Do I want to work through them again? Not really. But I'm happy to talk you through the ideas and do like simple examples in like a scratch buffer so we can see what I'm talking about. Oh my gosh, I forgot just how painful this was. This took me a long time to work out the first time. Oh yeah, there's print stuff to be fixed. Range overlapping with character. Oh yeah. So you have a range and you're removing a single character from it. Then you have to break the range into two ranges, and maybe one of the ranges or both of the ranges becomes a single character instead of a range of characters. All very fun. So many special cases when you do it this way, but once you have it done, it makes a few things very possible. Very interesting things become possible. So I'm not going to change the way this stuff works. But yeah, that was actually one of the big, I think, breakthroughs for me was when I started considering character matching any character and the inclusion and exclusion sets all as the same thing. A lot of this changed the way that I actually approached a lot of the problems. That realization. Oh, goodness. I'm just cleaning up if B is a range. Oh. Really mindless phase of moving old code over. Coding style has changed over the years, so apologies. Oh, goodness. Did you run a bad auto format rule or something? Changed over time. Yeah, so way back in the beginning days of my career, I was in the always put brackets no matter what, and always align brackets vertically camp. I've changed. I think the old software was a combination. I finally started to do, if it's a single line, then don't put brackets. But yeah, I've been compressing my code more and more as problems I work on become more complicated. So maybe I should just auto format things, but I've never found an auto formatter that I liked. They all just don't quite view it the way I want. There's always one little thing that's like, well, why do you format? Like they assume that because you want things intended this way with that construct, that you want this other construct to have these indents and so forth as well. It's like, no. No, I want this one to look different from that one. That's why I do it this way. So, I don't know. Maybe if I found the right one. So, yeah, so what we're doing is we have sets of characters. So if you have a single character in your regular expression, it's just the letter A. And it's an inclusion set, meaning when you check your character, check it against the character A. Also, we can have these ranges and things. We can have the negative character, minus sign, lowercase, uppercase, underscore, and plus in this inclusion set, right? In regular expressions, if we put this caret sign at the start of a set, it means none of these characters, anything that's not this. So we wrote a general class years and years ago, I did. That was what I called Clusion, right? Because I treat the characters the same way. It's just a Boolean whether it's to include all these characters or to exclude everything but these characters. And then I have the set of data. So a lot of this I've copy pasted over because frankly, re-engineering this isn't worth it. I did a lot of work on this before, got it all working, and now I can do a number of different operations very quickly. Not quick, well, whether it's computationally quick or not, I don't care. This is not the part that needs to be officially optimal. I'm sure some are configurable, but I haven't tried to configure them. Yep. Well, yeah, every time I've tried one, I've started configuring it and changing this setting, changed things I didn't want, and changing those things. It just, my mental model didn't align with their mental model about how code should be formatted. There's always a few things that are closed that sort of work. I get frustrated and I quit. I just manually format everything after that. So there's ClusionSet. So let's add it to the make file and just see how bad we did. But this is necessary for the NFAState. Rule set. Okay, let's see how we did. I was spoiled at work with a very nice formatter, albeit not for C++. Yep. C++ formatters, man. The more features they add to C++, the harder it gets to have a good formatter. Makes me want a super fast and nice formatter for myself. Almost didn't worry about aligning anything, hitting enter, just control, save. Yeah. Yeah. Update buffer. I don't remember what that's for. So we're just going to comment it out until I remember what it's for. Value. I don't need to check the value. I have already overridden the operator. Adjacent, yes. So one question is this letter and this letter next to each other? And that gets more complicated when you use UTF-8. So we've not copied this functionality over, but now we have to. Okay, so adjacency tests, we'll have to go in. Ugh. Actually, let's do it this way. Search, let's see here. Search for this. Const. And that should fix most of those issues. Not sure why I'm passing in print stuff as a Boolean parameter, but you know. Adjacency. Then to bump up, bump down. Yep, we'll have to do those with the adjacency. We'll bring that in. Talk about why I'm doing it. Are you going to support UTF-8 in your regex? Yes. That is the reason it's taking us so long to get through here. We've got to build up our NFAState to add to our NFA. And an NFAState needs these ClusionSets to keep track of all my regular expressions for me in UTF-8. So when you say \s for white space in your, so here, for those who are not regex masters, \s is a special character in a regular expression, meaning white space. So you can say hello world, and it would accept any string hello space world, not put there, or hello world or a tab. But I've never run into a regular expression engine that would accept hello world ampersand nbsp semicolon world, which means if you copy paste code off the web, it won't catch that as a white space. A non-breaking space is a Unicode character. And that drove me absolutely bonkers for every time. So my most recent job, people would keep saying, "Oh, this such and such tool is broken," and I'd grab their config file in YAML, and I'd open it up, and there would be a non-ASCII character at the start of every line because they copy pasted off of a web page. And for whatever reason, the YAML parser didn't know how to handle non-breaking spaces. Go figure. So yes, our regular expressions will handle non-breaking spaces and Russian characters and Japanese katakana and all that junk. If you want, bump down, bump up. Here's another value reference. Okay, let's see here. Dot value semicolon with dot value friend semicolon. We'll see how many. Oh, that was it. That was the last one. I'm adjacent. Bump up, bump down. Oh, that's it. We're almost there. UTF-8 character reference. source UTF-8 character reference dot. Oh, not this one. From the old one. Compiler core. This is basically back in my. I was experimenting and working out how it all needed to work. So we have these three functions that we did not port over. UTF-8 character reference CP and adjacent. Bump up, bump down, which is a scary thing, and we'll talk about that in a second. Wrong one. UTF-8. UTF-8 reference.cp and source directory. Advance. Right after advance. This basically lets us say we need an unpacked value. One more thing to steal on. Parsing C++. Are you going to support? Yes. Ooh, very neat. Yeah, I know. Super fun. Can't wait to use emojis as variables. Yes, you can write an entire programming language that uses the domino symbols from your favorite font. We had a test earlier today where we iterated over a UTF-8 string with Cyrillic alphabet, Greek alphabet, Japanese. I don't know if it's katakana or hiragana. I don't know the difference. And we included the domino characters. So, yeah, Egyptian hieroglyphs, if your font supports it. Lots of fun things we'll be able to do. Okay, so let me talk about adjacency in UTF-8. This page, this thing, I know that there's a place in the Russian alphabet that does this. Where did it go? Where are UTF-8 characters, you can't test for adjacency using the values themselves. Where's my Russian characters? There's Greek, here's Russian. Aha. Okay. Where's the thing? So I need to share the browser. Okay. If we're asking, is this character next to that character, in ASCII, it's easy, right? It's just, is the difference 1? You know, B minus A equals 1. Period. But in Russian, and probably all over the place actually, there are discontinuities which would happen here. D0BF. So this, the letter lowercase p next to the lowercase letter r, D180. These are not adjacent numbers because of the way that we encode UTF-8. So we have to extract the code point from these two patterns to make the adjacency comparison. Then, if we decide that two letters are adjacent and we need to bump one up or down to be so that we can close the gap, we have to add or subtract from the Unicode code point that we decoded and then re-encode it back into this 2-byte form. Does that make sense? Questions? Confusion? But yeah, lowercase p and lowercase r is a prime example of exactly this happening. It happens other places, but this is an easy one within the same alphabet, where you might actually do these things. So if there's still confusion about that, we can right to left CPP for once. Right to left. You know, I have not considered that. I'm pretty sure that's way over the line. Way over the line. Not allowed. Can't do it. Actually, you know what? What am I saying? I'm left-handed. I have ink and pencil graphite smeared all over my left hand for years because our language is left to right. You're right. Let's go right to left. screw this. I don't want to have my hands smeared with ink. All you righties out there, you can smear your hands for once. Of course, that's up to your text editor, not to the parser. Okay, so I need this unpacked value from the other place. So UTF-8 character reference. We're gonna just steal it. 8 charref H P and V and V. You have to be able to unpack a UTF-8 value to a Unicode value. That's private. Nobody needs to see this crap. This is not good. And then UTF-8 charref and V and V. Oops. Unpack. There we go. Unpacked value. Pack the value. UTF-8 character reference source. Way down at the bottom. Okay, so let's talk about this. Remember that encoding I said where the front so many characters, bytes of your character, have to be special bytes? Well, if it's a 2-byte character, we're stripping off some of that information. If it's a 3-byte character, we're stripping off other information. We're stripping out the what's it called? The continuation bits. That's what this does. It strips out those special bits from our value. And I lined things. I don't know. Maybe that looks funny to people. That's fine. Then when we want to pack that value back up, so if we wanted to iterate and say, where's my browser? Turn on the browser. So if I wanted to increment from P to R, I have to decode this, add 1, then encode that result. That's the only way I can go from here to here smoothly. Now, I don't want to do that all the time. I only want to do that within my parsing engine. This will not be a feature that we will put out in the future because that's not useful. It's only for our internal use. So eventually we're going to generate code like this that will ship out with your parser, your tokenizer, but it will not include these functions. These are special. This does assume that you're not being a complete idiot. So incrementing from Russian lowercase p to Russian lowercase r is valid because they're both 2-byte characters. But in the break between 3 and 4-byte characters and 2 and 3-byte characters, maybe somebody's doing something stupid and we're iterating and we're incrementing in between sizes like that. I mean, the odds of that are astronomically small, and I'm not even sure that there are valid ranges at the ends of the 2-byte, 3-byte range that you would want to work with, but I mean, maybe I could assert it, but we're just assuming we're not resizing the character. That's the rule. With those changes in, oh yeah, okay. Switch m underscore byte size. We did not call things like we did. And value becomes m underscore value. Oh, compile. Oh, that's an interesting one. Okay. So when we unpack the value, we just return whatever. When we pack the value back in, we've changed our value. If there's an error doing it, Well, interesting. Is valid equals true? So maybe we don't have a default. We assume everything is hunky-dory. Thinking I don't like this indentation stuff. So let's just clean this up a little bit. All right, see where our new errors are. Char size not implemented. Yes, you are entirely correct. Oh, shoot. Yeah, let's lay this one back up too. Why not? This is all just bitwise operations. If you have questions, I'm happy to talk through and clarify what we're doing and why we're doing it. Oh, it compiled. Amazing. Okay, so we have NFAState is now ready to accept a ClusionState called Clusion, because ClusionSet contains a flag boolean. Pretty sure. Oh, no, it doesn't. Oh, I wonder what you're. A ClusionSet. I must store that in the NFAState then. NFAState must have. Oh, I know why. Inclusion or exclusion. Character or any. So all of these are inclusion sets. Just this one is hidden as a single character, this one is hidden as the exclusion of nothing. I think I like the creation and removal of all these inclusion sets. We'll just make one. Yeah, this is fine. Again, I'm not really concerned with performance here. This part does not have to be fast. Only what we generate as output must be fast. That's the rule. Do need those. Still don't remember what update buffer meant. Oh, NFAState. That's cool. Is it not? It should be. Oh, op names. Okay. Op names with operation names. Index was not declared. That is true. Is start I have two different format strings plus so it's the index, which we don't need here. So this is rule ID and token. NFAState. Do I want the state ID? So we removed int index, but I'm not sure that we needed to. It gives us a way to talk about those. Yeah, okay, let's put it back in. Let's put index back in. So NFAState. Int state ID is what I want to call it, not index. State ID. I think that was my problem. I saw the word index, I was like, I use that when I'm counting through. Clear visited. Okay. We've got a lot of the underpinnings we need. Oh my gosh, what time is it? 5:30? Oh, yikes. So this one, you know what? I need to clean up some buffers. I'm getting different versions from different places. I want to keep the B and B. Actually, this one's going to go away. Oops. This one can go away. I think we've got everything out of UTF-8 character reference that we want. B and B, I'm pretty sure we've got everything we need there. NFA compiler, we will want to keep around. Inclusion rule can go away. Okay, this one, we actually don't want here. Tokenizer Generator can go away. So what we want is compiler core B and B. NFA. This is what we think an NFA looks like. I don't want to be a friend. I just don't. I'm nobody's friend. Is clear. Tell me what pattern you have. Log yourself. NFAState. Root state. And all the states. Text buffer. Okay. I don't think I want to make any constantness claims around that. NFA, that's CP. Okay, root state is null, our buffer is null. Clear. If the buffer is not null, delete the buffer. That's fair. Actually, these buffers are not the full file text buffers. This is a fragmented piece of buffer. For each state, in states, delete the state, then clear it. Root state was in that list, so it gets set to null. Is clear. That seems like it's unnecessary for test, for, like it's, we can get the same information. Pattern, we do want the pattern. Yep. Log. Empty, NFA, etc. Okay. Clear, visited. Okay, well, this looks bad. Big file. See how we do. We could type the word include, that would help. Is clear no longer exists, which is fine because root state equals null pointer. If that's really the only place that we use that, check. Okay, so we're compiling. Woo! Now, we have most of the pieces that we can build on, plowing through the pattern string to build up. Goodness. You know what we should do? We should do a quick little update and a git save while things are compiling. Copied some functionality. Oh, various functionalities from old code. Compiler core BMB. Basically, sandbox. UTF-8 character reference. Basically stole NFA. Basically stole NFAState. ClusionSet. Conclusion rule. I think that's most of what we stole. And those are big enough, complicated enough pieces of the software that I don't want to rederive them from nothing. So I think it's okay. If you disagree, let me know. Things compile untested. Status, git add, all sorts of things. Collision rule, ClusionSet, NFA. Yeah. We started building out the converter. And stole code from old sandbox. Okay, so back to pattern NFA converter. Init. What does init do for me? What was my thought there? Oh, okay. Well, honestly, this can change. Pattern. Privately, we need a text buffer. And we can just not make it a pointer. This is pure static. Fine. Should be fine. Buffer dot reference text from the pattern. So it doesn't do a deep copy, it doesn't own it. And when the text buffer gets a new thing, clear. If we don't own the contents, we don't delete the contents. So this will not take long at all. File reference text, get the label. Okay, so I need the label as well. Pattern. Okay. So that's our init function, which honestly, it's a one-line function. Why clever? Okay. NFA. Okay. So scan pattern has to return result equals true. Return result. It will return all the fragments it can find. Reduce. We need to reduce fragments. So let's see here. So I don't remember what those do. Reduce calls these reduces. Not that much. Talk about what reduce does in a second. I'm 99% sure the NFA compiler. Let's see. Reduce does that, asserts that, and empties the fragments completely, returning the fragment. There, that's basically it. So this one does that, and then returns the root fragment. Okay, so that should file as far as that goes. Oh, okay, well, it's about time for me to call it. If I go too long, it's a big file and I have to split the video for Rumble. So we're probably going to pause here. Building up the little pieces we need just to read through an NFA pattern. But it's okay. We're going to get something really fast here. So thanks for joining me. Hopefully you have a good weekend. On Monday, we'll be back to game dev. We probably will try to fix the audio pop some more. And yeah, that's basically where I'm at. So thanks for joining me today. Thanks for the chats. And everybody have a wonderful day. Bye-bye.